Have you ever imagined traveling between the stars? On paper, it sounds poetic sailing across the cosmos to reach new worlds. But the reality is far less romantic. For example, NASA's Voyager 1 spacecraft, the fastest probe we've ever launched, moves at about 10.5 miles per second. Even at that incredible speed, it would still need nearly 75,000 years just to reach our nearest neighboring star, Proxima Centauri. Now, let's dream bigger. Suppose one day humanity builds ships that can approach the speed of light around 186,000 miles per second. It sounds like science fiction, almost impossible. But even then, escaping the Milky Way galaxy would take close to 100,000 years. And that's only if we wanted to leave our galaxy. If we dared to think even further to attempt intergalactic travel then, we'd face a problem far stranger than just distance. In 2013, scientists discovered something deeply unsettling. A colossal cosmic void surrounding our galaxy. According to physics, it shouldn't even exist. This isn't just a region with a little less matter. It's one of the largest voids ever found in the universe, possibly stretching 2 billion light years across. To put that in perspective, it could hold over 20,000 galaxies the size of the Milky Way lined up side by side. Light itself would need 2 billion years to travel across it. But the size isn't the most shocking part, it's our location. Evidence suggests that the Milky Way sits near the very center of this vast emptiness, like being at the heart of a cosmic funnel. If that's true, it could completely reshape how we understand the universe's structure. And that leads to an unsettling question. What lies beyond this void? Could the regions outside be built differently, denser, stranger? Perhaps even following different physical laws than the ones we know? This mysterious region, now called the KBC void, or the local hole, was first suggested by astronomers Ryan Keenan, Amy Barger, and Lennox Cowie. When they proposed it, the idea sent shockwaves through the scientific community. This wasn't just another patch of thin space, it challenged the very framework of cosmic order. But what exactly is this void? And why does it matter so much? To answer that, we need to rewind the clock all the way back 13.8 billion years to the beginning of everything, the Big Bang. Back then, the universe expanded outward instantly in all directions. Energy and matter spread like ripples across a pond. According to the cosmological principle, matter should have been distributed evenly, meaning that on the largest scales, the universe should look the same everywhere. The same laws of physics here on Earth should apply to galaxies billions of light years away. But modern data suggests otherwise. Matter isn't perfectly spread out, it clumps in some regions, thins out in others, and the KBC void is the most extreme example of this imbalance. A region so massive and so underpopulated that it might even obey physics differently. Estimates suggest this void is roughly 1 billion light years in radius 4 times larger than the Laniakea supercluster, which holds about 100,000 galaxies, including our own. That makes the KBC void the largest known empty structure in the universe, accounting for nearly 2% of the observable cosmos. But here's the twist, it's not completely empty. We're inside it! According to astrophysicist Indra Burnich from the University of St. Andrews, matter inside this void star's galaxies, everything is about 20% less dense compared to areas outside. That may sound like a small drop, but at this scale, it's extraordinary. And strangely enough, this bizarre emptiness might help explain one of the biggest mysteries in cosmology. Why the universe is expanding faster than expected after the Big Bang, the universe began expanding again. It still is. The rate of this expansion is called the Hubble constant, and scientists use 2 main methods to measure it. The first method involves nearby cosmic objects like supernova and galaxies. By tracking how quickly they move away from one another, astrophysicists calculate an expansion rate of about 45 miles per second per megaparsec, meaning galaxies 3 million light apart drift an extra 45 miles apart every second. The second method looks much deeper at the cosmic microwave background, the faint radiation left over from the Big Bang. This light has traveled for over 13 billion years, acting like a fossil snapshot of the infant universe. And here's where the mystery begins. From those measurements, scientists calculate how quickly the universe should be expanding today. And here's where the mystery deepens. The second method, which uses the cosmic microwave background, gives a rate of around 41 miles per second per minute, noticeably lower than the 45 miles per second calculated from nearby galaxies. This mismatch is known as the Hubble tension. If we trust the early universe data, then the cosmos should be expanding more slowly than it actually appears. Yet, direct observations tell us that galaxies around us are drifting apart about 8% faster than those predictions allow. The cause remains hotly debated, but a growing number of astrophysicists think the answer may lie in our own neighborhood, within the KBC void. And the key could be gravity. We know gravity makes massive objects pull on smaller one-stars, tug on planets, planets tug on moons. On a cosmic scale, denser regions outside the void may be pulling on the galaxies inside, almost like they're dragging them outward. That extra pull could be accelerating expansion inside the void, adding speed on top of the universe's natural growth. Cosmologist Brian Keating from UC San Diego believes this is a real possibility. The void hypothesis could help explain why expansion looks faster than expected, but he also admits many questions remain unanswered. For instance, how far does the void's influence reach? If it only affects our local region, then the Hubble tension remains unresolved on a universal scale. Another challenge is that models of the void differ. Some predict strong gravitational effects, others weaker ones. Reality could be far more complicated than any simple diagram. And recent data suggests the void might be smaller than originally thought. A team analyzing the cosmic flows for a catalog, which contains the largest set of galaxy distance measurements, used the Tully-Fisher relation comparing a galaxy's brightness with its spin, and found the void might measure only about 230 million light years across, almost 10 times smaller than earlier estimates. If true, that would mean the void's gravitational effects can't fully explain the discrepancy in cosmic expansion. The void still exists. Scientists are fairly certain of that, but whether it spans 2% of the observable universe or something much more modest is still unclear. Even more intriguing, new ultra-precise maps from the DESI Project 2023 to 2024 suggest that voids like this aren't rare at all. Our local hole may just be one of many across the cosmic web, not a unique structure. But that doesn't make things any less exciting. On the contrary, the KBC void raises even more profound questions. What if we weren't inside? And what if humanity were observing the universe from the outside of this void? Would galaxies appear differently? Would the expansion rate look more uniform? Could our very perception of the universe change? The problem, of course, is distance. The boundaries of this void are so far away that humanity may never physically reach them. But let's imagine for a moment that we could. Suppose we had technology allowing limitless speed and endurance, pushing beyond the current limits of physics. What would a journey to the edge look like? First, we'd need a spacecraft unlike anything ever built. It would have to handle immense acceleration forces and protect its crew from one of the deadliest dangers of deep space: radiation. But most importantly, would need unimaginable speed. Take today's fastest probe, Voyager 1, moving at about 10.5 miles per second. At that pace, it took 35 years just to leave the solar system, and it would take about 74,600 years to reach Proxima Centauri, our closest star. Hardly inspiring for intergalactic travel. So, let's imagine instead a ship with powerful radiation shielding, far superior speed, and virtually unlimited time. Of course, acceleration can't be instantaneous. Movies like Star Wars show ships jumping to light speed in seconds. But in reality, that would mean experiencing forces of over 6,000 grams, enough to squash a human flat. The body can only handle about 4 to 6 grams for short bursts before blood flow to the brain cuts off. So, a gradual acceleration is the only way. Let's say our ship accelerates gently, gaining 1 meter per second of speed every minute. After 10 minutes, it's moving at 10 meters per second. After an hour, 60 meters per second. It builds steadily. With this method, in about 13 and a half days, the ship would already cross the boundary of the solar system, where the sun's influence ends and interstellar space begins. That's astonishing compared to Voyager 1 and 2, which needed 35 and 41 years to get there. By then, the ship would be traveling at nearly 19,300 miles per second, about 10.2% the speed of light for human standards. That's breathtaking. But even at those astonishing speeds, on the cosmic scale, you're still moving at a crawl at the far edge of the solar system. Communication with Earth becomes painfully slow. A radio signal racing at light speed takes about 17 hours to get back home. Another 17 hours for a reply. That's 34 hours for a single exchange. Hardly a conversation more, like sending a message and waiting a full day in silence for a response. As your ship pushes farther into the dark abyss, the sun fades into just another bright speck among billions. Meanwhile, your speed continues to climb. After about 65 days, you're moving at half the speed of light, around 93,000 miles per second. At this point, you're roughly 260 billion miles from Earth. By human standards, that's unimaginably far. Yet cosmically, it's tiny, only about 4.4% of a light. But at this speed, Einstein's predictions about relativity come alive. Time dilation begins to take effect. To an observer on Earth, 65 days have passed. But on your ship, less time has slipped by. Your onboard clock ticks slower than Earth's, and the faster you go, the stronger the effect becomes. At 50% of light speed, every 10 hours on Earth equals only 8.5 hours aboard your ship. Still, if your goal is the KBC void, half light speed isn't enough. So the ship keeps accelerating. Soon, you're at 90% of light speed, 168,000 miles per second. Now, time on board runs at less than half Earth's pace. Every hour on Earth feels like just 26 minutes to you. Time itself has turned into your ally. On the 129th day, something extraordinary happens. The ship passes the 1 trillion mile mark and reaches 99.99% the speed of light. Going any faster is impossible. The speed of light is nature's absolute limit area, built into the very fabric of space and time. Only massless particles like photons and gravitational waves can achieve it. Anything with mass would require infinite energy to cross that threshold. The Large Hadron Collider demonstrates this vividly. Protons, they're all pushed to 0.99991 C, just a hair below light speed. At that point, they're moving only 3 meters per second shy of the cosmic maximum. And yet, giving them that last little push would require more energy than all the stars in the universe combined. The barrier isn't technological, it's fundamental. The speed of light isn't a target, it's a wall. Nature itself enforces this. In 1991, scientists detected the legendary Omega particle, a subatomic particle traveling so close to light speed that its energy rivaled a 58 miles per hour baseball. Imagine something smaller than an atom carrying enough force to smash through a steel door. That's the terrifying reality of near-light travel. Energy skyrockets exponentially as you approach the limit. At 99.99% light speed, your ship becomes one of the most destructive objects imaginable. Its kinetic energy could rival or even surpass a supernova. But you can't go faster, according to relativity. At light speed, your ship's mass would become infinite. And to accelerate infinite mass, you'd need infinite energy. Physics itself collapses at that boundary. So, you remain at 99.99% of light speed and, now, time warps dramatically. Your onboard time slows by a factor of about 70 compared to Earth. To you, life feels normal, your heartbeat steady, your clock ticking, as usual, but to observers on Earth, you've become a fast-forwarded blur. Take Proxima Centauri. For light years away, from Earth's perspective, the journey lasts 4 years. But to you on board, it's just 21 days. Space itself contracts, and time bends in your favor, and the voyage continues. After about 1,400 years of ship time, you finally break free of the Milky Way galaxy. But on Earth, 100,000 years have passed. Humanity may be long gone. Civilizations forgotten yet. You keep traveling. Eventually, after covering 230 million light years, you reach your destination by your clock. About 3.25 million years have gone by. At last, the mysterious boundary of the KBC void looms ahead. Crossing into it, you notice the difference immediately. The density of matter begins to rise. Where galaxies once seemed scattered and sparse, they now cluster more frequently. Beyond this vast, empty gulf, the cosmic landscape changes sand with it. Perhaps the very fabric of the universe itself. As you move deeper into the cosmos, the scenery begins to change. Scientific models suggest that galaxies don't just scatter randomly, they cluster into chains, groups, and enormous superclusters. This is the large-scale structure of the universe. Space here feels heavier, more crowded. Not only does the amount of ordinary matter increase, but so does dark matter, the mysterious substance thought to shape and bind these cosmic structures together. With more matter comes stronger gravity, and now your ship requires far more precise navigation. This is no longer the silent emptiness of the void here. Everything tugs, pulls, and collides with everything else. But even this vast, busy network might just be the surface layer of something greater. Hidden beyond the visible is a mystery so deep we can barely grasp it. The universe is larger, older, and stranger than we can currently comprehend. Right now, astronomers estimate there are 100 to 200 billion galaxies we can detect. Yet, it's entirely possible that there are 2 trillion or more inside our observable universe, alone most of them invisible to us. We know the observable universe is about 13.7 billion years old. Defined by the distance light has had time to travel since the Big Bang. By measuring light from the oldest stars, cosmologists determined that the farthest photons we can currently see have traveled for around 45 to 47 billion years. That makes the diameter of our observable sphere about 93 billion light years across. To put that into perspective, a single light year the distance light covers in 1 year as 9.46 trillion kilometers. Now imagine multiplying that by 93 billion. But this raises a puzzling question. If the universe is only 13.7 billion years old, how can we see a region 93 billion light years across? The answer lies in the fact that space itself has been expanding ever since the Big Bang, stretching faster than the light racing through it, which also suggests something incredible. The universe might actually be much older than 14 billion years, and vastly larger than what we can ever observe. Anything beyond the cosmic horizon, the limit of light that has reached us, remains hidden. We can't see what lies beyond because the light hasn't had time to arrive. To us, it's simply blackness. But that doesn't mean nothing is out there. The cosmos has been expanding since its fiery birth. Edwin Hubble first discovered that galaxies are all racing away from us, and the farther they are, the faster they retreat. For every additional megaparsec of distance, galaxies move away about 500 kilometers per second faster along, now known as the Hubble constant. The observable region shaped by this expansion is called the Hubble volume. But observable doesn't mean limited by our technology. It means limited by the speed of light itself the fastest. Anything can move. When we gaze at the night sky, we are literally looking back in time. Every glittering star is a memory of how it looked thousands, millions, or even billions of years ago. Some starlight hitting your eyes tonight may have started its journey before humans even existed. If something lies beyond the observable boundary, its light simply hasn't reached us yet. That invisible region defines the cosmic horizon, the furthest edge of the universe we can currently retrieve information from. But is there more beyond it? Almost certainly. The big question is, how much more? Astronomers study the curvature of the universe to get clues. If the universe curves like a sphere, it has a finite size. If it curves like a saddle, it could be finite in another way. But if it's perfectly flat, then it could extend forever. Current measurements suggest the universe is astonishingly close to flat, like a sheet of endless paper. If that's correct, then the universe doesn't end. It stretches on without limit. And if it is infinite, the implications are staggering. It wouldn't just contain more stars, more galaxies, and more planets. It would eventually contain every possible arrangement of matter. That means somewhere out there could be a solar system identical to ours, with an Earth exactly like this one. And yes, an alternate version of you. The only difference, maybe your cosmic twin chose to eat cereal for breakfast today while you didn't. Some cosmologists suggest that if the universe truly is infinite, then somewhere out there, beyond unimaginable distances, there might exist another Hubble volume identical to ours, complete with a version of you mirroring your every action. Well, that sounds impossible to wrap our minds around. The universe continues to surprise us with discoveries that seem just as unbelievable. Back in 2008, astronomers noticed something extraordinary. Clusters of galaxies drifting together in the same direction, moving at speeds of over 3 million kilometers per hour. This strange phenomena was named dark flow. Why is it so unusual? Because according to everything we know about how matter should have been distributed after the Big Bang, galaxies shouldn't all be streaming one way. Something unseen, something beyond the edge of our observable universe appears to be pulling on them. One possibility is that colossal structures lie outside our cosmic horizon, exerting their immense gravity. Perhaps unimaginable aggregations of matter and energy we can't detect. Or perhaps forces from entirely different universes. But even within the observable cosmos, we've found structures that challenge our understanding. The largest known of them all is the Hercules Corona Borealis Great Wall. Stretching across 10 billion light, it takes up about 11% of the observable universe. To grasp that scale, imagine traveling at the speed of light fast enough to circle Earth 7 times in a single second. Even at that speed, it would take you 10 billion years just to cross this one structure. And here's the mystery. It shouldn't even exist. Our current models can't explain how something so massive could have formed only a few billion years after the Big Bang. Yet, there it is, hinting that the universe may build giants we never thought possible. Some scientists even speculate such cosmic titans could warp, bend, or one day tear apart the very fabric of space. And what if our universe itself isn't the only one? A bold idea suggests that in the aftermath of the Big Bang, space didn't just expand, it formed bubbles. Each bubble became a universe, sealed off with its own laws of physics. In this model, not only is space infinite, but each bubble is infinite, too housing infinite variations of infinity. But even if other universes exist, there's a catch. The space between bubbles keeps stretching. No matter how fast we traveled, we could never reach another bubble. They are forever separated from us. That brings us back to the question, will we ever see beyond the edge of our own cosmic horizon? Sadly, the answer seems to be no. Light from beyond our Hubble volume will never reach Earth because the space between us is expanding faster than light itself. This isn't a technological barrier, it's a physical one. Still, our window into the past is widening. As time passes, photons from distant galaxies have more time to arrive, slowly increasing the size of the observable universe. Yet at the same time, expansion pushes galaxies farther and farther away. Some regions we can see today will eventually slip beyond our reach forever. That's why telescopes, like the James Webb Space Telescope, are so important, acting like a cosmic time machine. They allow us to peer deeper into space and further back in time than ever before. Perhaps, one day, they'll give us new clues about what lies beyond. So, what do you think? Is the universe infinite? Could there really be another version of you, billions of light years away, making different choices right now? The truth is, the deeper we look, the stranger and more mysterious the cosmos becomes. And maybe the answers lie just beyond the horizon.